So we know this is an amino acid with its alpha carbon, its amine group, its carboxyl group, and its R group. And we know these are ionizable groups, which means they can act as acids, where they can either be in their protonated forms or they can be in their deprotonated forms. So therefore, we know they're acids, so therefore they must have pKa's. This guy has a pK of 2, this guy has a pK of 9, and this guy has a pK of 4. So now that we know this, how do we determine whether these functional groups are protonated or deprotonated? Well, again, in the last video, we explained how it's the pH of the solution that determines whether the functional groups are protonated or deprotonated. And in the last video, we explained about this neat trick where we can compare the pH of the solution to the pKa of the functional group to determine whether the functional group is protonated or not. For example, let's say we have a pH of 7. If we have a pH of 7, will these functional groups be protonated or deprotonated? Well, again, we know. For example, this functional group, as long as we know the pK of the functional group and we compare it to the pH of the solution that the functional group is in, you can determine whether it's protonated or not. And we know if the pH of the solution is greater than the pK of the functional group, it's in its deprotonated form. It's unprotonated form, and we see that with this simple trick. So again, if you know the pH of the solution, you can compare the pH of the solution to those pKa's of those functional groups to determine whether the functional groups are protonated or deprotonated. But what if we had a tricky example? What if we had this polypeptide? This polypeptide with all these different amino acid residues, with all these different ionizable groups that can act as acids. Well, again, it's the same idea. It's the same idea. We know they're ionizable, so we know they can be in their protonated form or they can be in their deprotonated form. So again, this is what they look like deprotonated. This is what they look like in their protonated form. So again, because they're acids and they can be protonated or deprotonated, we know they have pKa's. And these are the particular pKa's of these functional groups. So now that we know this, now, for example, if we have a pH of 7, if we have this polypeptide and a pH of 7, will these functional groups be protonated or deprotonated? Well, we know how to do this. We already learned the rule. If we know the pH of the solution, we can compare that pH to the pKa's of the functional groups to determine whether they're protonated or not. So you can try it for yourself, and once you try it out for yourself, you'll see that this guy would be deprotonated. This guy will be protonated, this guy will be protonated, this guy will be deprotonated, etc. Because again, as long as you know the pK of the functional group and compare it to the pH of the solution and use this simple rule, you can determine whether they're protonated or deprotonated. And something important to realize is this carbon hydrogen is a very weak acid. This is a very weak acid with a huge pKa. So it's essentially unionizable. It will always be protonated, so we can kind of just ignore this. So even though it's an R group, it's essentially a weak acid, so it'll always be protonated, so we don't need to worry about it. So now that we know this, and now we know at a pH of 7, this is what this compound will look like. Now, how do we determine what the isoelectric point is? And we know what the isoelectric point is. We know there'll be a certain pH that will render this polypeptide neutrally charged. Though there will be a certain pH where the net charge of this polypeptide will be 0. So how do we determine the pH when this polypeptide is 0? And we know that pH that renders this polypeptide neutrally charged is referred to as the isoelectric point. So what is the isoelectric point of this polypeptide, the pH when it's neutrally charged? Well, to determine that, we use this simple trick. First thing we do is we take every functional group and we protonate it. We put it in its protonated form. So that's step 1. Protonate each functional group. Once you do that, you see what the net charge is. So once we protonate all the functional group, we see the net charge is positive 3. We have 3 positive charges. So that's step 1. The net charge when all the functional groups are protonated. So we see that's positive 3. Next step is you take the pKa's and you write them in ascending order. So we know these are the pKa's. So we take all these pKa's and we write them in ascending order. So again, step 1, protonate all the functional groups and see what the net charge is when all the functional groups are protonated, and that was positive 3. Next step is you draw the pKa's in ascending order. Now you just do this simple trick where this is positive 3, then you do minus 1, so this is positive 2, then minus 1, so this is positive 1, then minus 1, this is 0, minus 1, negative 1, minus 1, negative 2. So now that we've done this, now we know everything we need to know. So why do we go through all the work to do this? Well, now this is really interesting. Now we can take any random pH. So I'm just going to throw a random pH of maybe 4. At a pH of 4, what will be the net charge? Well, we say at a pH of 4 will fall under this range, so the net charge will be positive 2. So that's interesting. If we had a pH of 4, you could do this operation, and you will see the net charge would be positive 2. But let's do another example. Let's say we have a pH of maybe 7. If we have a pH of 7, what's the net charge? Well, we see a pH of 7 will fall under this range, so the net charge will be positive 1. So at a pH of 7, the net charge will be positive 1. And we see at a pH of 8.5, the net charge will be 0. So that's the isoelectric point, around 8.5. That's the pH that will render this polypeptide neutrally charged. What about a pH of 13? If we have a pH of 13, what's the net charge? Well, pH of 13 will fall under this range, so the net charge will be negative 2. And you could try it. You could try a pH of 13, compare that pH to all the pKa's, and you'll see the net charge of this polypeptide will be negative 2. So now we know. Essentially what's going to happen. We know under this range, at a pH of around 8.5, the net charge will be 0. So we know that's the isoelectric point. The isoelectric point of this polypeptide is 8.5. It's the pH when this polypeptide will be neutrally charged. And again, we can try it. And again, I know there's a lot of stuff going on here, but the point is at a pH of 8.5, we compare that pH to the pK of all these functional groups. So again, this functional group had a pK of 8. So we compare that to the pH of the solution it's in. And when the pH is greater than the pK, we know it's deprotonated. So this guy will be in its unprotonated form. So again, so now you just keep doing that and compare these pKs to these pHs, and you see at a pH of 8.5, you can add up all these charges. You can add up all these charges, and you'll essentially see at a pH of 8.5, you can do this operation, and you'll see we have a negative charge here, a positive charge here, and a positive charge here. So the net charge will be 0. So we see at a pH of 8.5, the net charge will be 0. So therefore, 8.5 is the isoelectric point. It's the pH when the net charge of this polypeptide will be 0.